In this problem, we're told the switch opens at t equals 0. Use the Laplace transform to find I of t. And we're going to utilize our problem solving strategy entitled the Laplace transform of transient circuits. Step 1 in that says to assume the circuit's in steady state at t equals 0 minus. Draw the circuit, replace the capacitors with open circuits, the inductors with short circuits, and solve for those corresponding quantities. So here's our circuit at t equals 0 minus, and I've labeled the capacitor voltage and the inductor current at 0 minus. On both of those, if we look at the circuit, for instance, this current's 0, and we know that by KVL there's 36 volts across here, which says there's 9 amps here. This has to be 0, so if we apply KCL at that node, we get IL of 0 minus, which we know is equal to IL of 0 plus, which is IL of 0 is 9 amps. And now if we do KVL around this loop, we know there's 0 volts across both of those resistors. So then VC 0 minus equals VC 0 plus equals VC 0 equals 12 volts. So that completes our analysis at t equals 0 minus. Now step 2 says draw the circuit for t greater than 0. So here's the circuit for t greater than 0. And now we're going to apply KVL to this single loop circuit to come up with the equation. So if we start here and go around counterclockwise, we'll have 2 I of t plus for the capacitor we're going to have 1 over c integral from 0 to t I dt plus initial value, so we have 1 over 1 integral from 0 to t. Alright, this I of x dx plus vc 0 plus 4I of t, which is the drop across this resistor, plus the drop across the inductor is 1 di dt, and that's equal to 12. And we know, for instance, that this is equal to 12. So if we collect up terms here, we'll have 6I of t plus the integral from 0 to t I of x dx plus 12 plus di dt equals 12. And for instance, we can see, well, we've got 12 on both sides, so those just cancel out. Now we're ready for step 3, which says apply the Laplace transform. We've got our integral differential equation. So we had 6I of t, that becomes 6I of s. And here we have take the Laplace of the integral, so we have 1 over s I of s. Now we have the derivative, so we need the Laplace of the derivative. So we have s I of s minus I of 0 is equal to 0. And if we'll remember, the initial value is 9 amps. So that completes step 3. So now step 4 says, well, solve for I of s. So collecting up terms, we have 6 plus 1 over s plus s times I of s is equal to 9. And we have, if we multiply through by s, we get s squared plus 6s plus 1 times I of s is equal to 9s. So then I of S is 9S over S squared plus 6S plus 1. So that completes step 4. Step 5 says, well, apply the inverse transform to find our solution. So then in step 5, we have I of S is 9S over S squared plus 6S plus 1. Let's factor that denominator to find the roots. So we want to know what are the roots of this equation. So using the quadratic formula, we have minus 6 plus or minus the square root of 6 squared minus 4 times 1 over 2. So we have S is equal to minus 3 plus or minus 2.828. So our two roots are minus 0.172 and minus 5.828. So our partial fraction expansion then is K1 over S plus 0.172 plus K2 over S plus 5.828. And so now we're ready to do the partial fraction expansion. We've got it done. Now we're ready to evaluate the K's. So for instance, K1, we're going to multiply through by S plus 0.172 and evaluate at S equal minus 0.172. So here we have 9 times minus 0.172 over minus 0.172 plus 5.828. So then K1 is minus 0.2737. K2, then we're going to multiply through by S plus 5.828. And we're going to evaluate S equals minus 5.828. So here we have 9 minus 5.828 over minus 5.828 plus 0.172. So K2 is 9.2737. So now we've found K1 and K2. So then I of S is minus 0.2737 over S plus 0.172 plus 9.2737 over S plus 5.828. So then I of T is minus 0.2737 e to the minus 0.172t plus 9.2737 e to the minus 5.828t u of t amps. Now notice that our initial condition checks, we plug in t equals 0, we get 9, which satisfies our initial condition.